Today, we're talking about something pretty wild. We're going to break down how you build a brain, not for a person, but for the next wave of robots, the ones designed to walk and work and operate right alongside us. We're diving deep into the tech behind Advidia's Project GR00T, which is a foundational AI model for humanoid robots. All right, let's get into it. Whenever we talk about AI this advanced, especially robots that can move and act in the world, one question always comes up first. With robots that can do what humans do, are we all about to be out of work? It's a huge concern, and you hear it all the time.
But what if that's the completely wrong way to look at it? The source material for today's explainer flips that whole idea on its head. It suggests that actually, for a lot of the world's most advanced countries, the real problem isn't that there are too few jobs, it's that there are way too few people to fill the jobs we already have.
Okay, get this. This number, 4.2x, is really the core of the whole issue. A recent McKinsey report found that in the world's most advanced economies, jobs have been created 4.2 times faster than the available workforce over the last 10 years. That's not just a small gap, that's a massive structural problem. And it kind of sets the stage for why we might need a totally new kind of solution. And this growing labor shortage, it leads us right to our next big question. Why humanoid robots? I mean, the goal here isn't just to build something that looks cool out of a sci-fi movie. It's about tackling a very real-world problem that's happening right now. Just look at the industries that are getting hit the hardest by this shortage. We're talking healthcare, construction, manufacturing. They all share one critical thing in common. They're all about physical work. Using tools, moving things around, navigating real, messy spaces. A large language model like ChatGPT is amazing, but it can't fix this. This is where you see the urgent need for what's called physical AI.
So you might be thinking, okay, but why make them look like us? It's not about vanity. It's about pure, simple practicality. Think about it. Our entire world, our kitchens, our hospitals, our factories, every single space is designed for the human body. So for a robot to be a true generalist, one that can say, make you a coffee and then go cook some rice, it needs a body that fits our world. A specialist robot, like one that only makes coffee, is great at its one job, but it's stuck. It can't adapt.
All right, so the need is clear. But building these general-purpose robots, well, it runs into one gigantic roadblock, and it might just be the single biggest problem in all of physical AI: data. More specifically, the extreme lack of high-quality training data. This quote from one of the lead engineers on the project, it really says everything. The strategies that they came up with to solve this, they weren't just some cool ideas they had in a lab. They were created out of sheer desperation. They had to get creative. I mean, unlike AI models that learn from text, you can't just scrape the internet for robot actions. That library just doesn't exist. So their solution is this really clever strategy they call the data pyramid. Think of it like this. At the very, very top, the peak of the pyramid, you have the absolute gold standard, real-world data where a human is actually controlling a robot. It's perfect data, but it's super expensive and hard to get. Then, in the middle, you've got synthetic data, which is generated inside a simulation. You can make an infinite amount of it, which is great, but building those simulations to be realistic is a ton of work. And then you have the base, the huge, wide foundation of the pyramid, internet videos. Just think of every cooking tutorial on YouTube. It's a massive, almost endless resource, but the data is all messy, it's unstructured, and a robot can't just use it. At least, not directly. Okay, so once you have a strategy to get the data, the next huge piece of the puzzle is building a brain that can actually use all that different data to think and act in the real world. And the way the GR00 model is designed, its architecture, is where things get really, really smart.
The model's whole structure is inspired by that famous book by Daniel Kahneman, Thinking Fast and Slow. So it has two systems working together. You've got System 2, which is the planner. This is the slow, deliberate part of the brain. It takes a big, complex command like pick up that object, and it breaks it down into a series of small, simple steps. And then you have System 1, the executor. This is the fast, almost reflexive part that moves at an incredible 120 Hertz, that's 120 times a second, to carry out those simple actions smoothly and efficiently.
At the very heart of that slow-thinking planner is something called a diffusion transformer.
Now, this is the same kind of core technology that powers image generators like DALL-E. But instead of generating a picture from a text prompt, it's generating a plan of action from all sorts of inputs: what the robot sees, the command it was given, and its own physical position. It's what lets the robot make sense of a messy situation and come up with a coherent plan.
But a plan is just an idea, right? You need a way to turn that plan into actual physical movement. And that's the job of the action decoder. You can think of it as a universal translator. It takes the general plan from the main brain and converts it into the exact motor commands needed for whatever specific robot body it's connected to. This piece is absolutely the key to making the whole model a true generalist.
And that action decoder is what enables one of the most powerful ideas in this entire explainer: the concept of one brain controlling many different bodies. It means you can take that same core AI, that same foundation of knowledge, and you can apply it to a super dexterous humanoid hand, or a big industrial robot arm, or maybe even new robot designs we haven't even dreamed of yet.
So how does this brain actually learn? The source material gives a fantastic analogy. The first way is imitation learning. This is kind of like having a cool older sibling. The robot just watches an expert human do something and tries to copy them exactly. It's really effective, but you're always limited by how much of that expensive expert data you have. The other way is reinforcement learning. This is more like being an only child. There's no one to copy. You just have to learn by trial and error, trying to get better and better to achieve a goal. This helps get around the data problem, but making what you learn in a simulation work in the real world, that sim-to-real gap, is still a huge challenge for researchers.
So, to bring it all home, this entire approach really stands on three main pillars. First, there's the data pyramid. That's their smart strategy for solving the huge data shortage problem. Second, you've got the dual system architecture, that fast and slow thinking brain, where the planner and the doer are trained to work together perfectly. And third, it's a generalist model, which, thanks to that action decoder, means one central brain can learn to control many different types of robot bodies for many different kinds of jobs.
And all of this, the incredible engineering, the undeniable progress, it all leads to this final thought. As this tech keeps getting better and starts moving out of the lab and into our world, it leaves us with one heck of a question to think about. If you have a robot that can learn to do basically any physical task, what's the very first thing we should teach it? Thanks for watching.